But enough on RPKI for now. We're going to talk a little bit more about network design and building, and we've got a good expert to guide us in that field today. We've got Mounir and Mohamed, who's been working for many years in the Cisco service provider team. I'm sure that those of you that run networks in this part of the world, this is no new person. You've known him from perhaps working with him or consulting with him through his work at Cisco. So without further delay, can I call you to the stage, please, Mounir? And you'll walk us through what it's like to run networks in this part of the world. Thank you.
So good morning, everyone, and thanks for sticking around and taking the time to attend this presentation. My name is Mohamed. I'm part of the global service provider team at Cisco, and I really have the pleasure to present for the first time at MENOG and to give you an update on SRv6 technology, architecture, deployment, as well as standardization. So at the beginning, we would like to take the opportunity to thank all the leading operators, all the ecosystem partners, all the academic partners for investing and adopting SRv6 or segment routing technology. And special thanks for the IETF working group as well as Cisco segment routing team for the fantastic achievement and milestone achieved over the last 10 years. We started the segment routing project back in 2012, June 2012. So today in 2020, we are celebrating the 10th anniversary of the segment routing project, which was a great success. So thanks to everyone who participated in this success. So since I have only 25 minutes, I wanted to leave you with a lot of resources and demos, tutorials for all the technology I'm going to cover in this presentation. So we always maintain the segmentrouting.net and keep it up to date with all the information about the technology. So I would highly recommend you to make it a habit to go to segmentrouting.net every once in a while to get yourself updated about the latest and the greatest information about SRv6. So at the beginning, let me start with a little bit of highlighting some of the aspects or main aspects of the segment routing or SRv6 architecture. So SRv6 allows us to carry services end to end in a very transparent way with the ultimate simplified control plane and data plane for both the overlay and underlay. So with segment routing, we can carry services packets or customer services, which could be IPv4 or IPv6, or could be VPNv4, VPNv6, or could be layer 2 VPN as well, the likes of the EVPN. We can carry it across the entire SRv6 domain with a very simplified encapsulation. That is just IPv6. So we take whatever packets we receive at the ingress point of the SR domain, and we encapsulate it with a simple IPv6 header, the header that you used to know, and we transport the packet across the network without even touching the inner packets or the inner payload or aspects of the customer traffic. And the use of IPv6 as a data plane with the segment routing policy or control plane architectures allowed us to basically do more things with less protocols. So today we have with the segment routing or SRv6 architecture, native inter-domain routing to stitch multiple domains together, things like the metro, connecting the metro to the core, to the data center, to the peering domain, and doing all of this without the need for hierarchical routing, the likes of the BGP-LU with LDP, with RFA. All these complex protocols have been eliminated by the segment routing architecture. Also, we have native ECMP capability embedded into the protocol, the use of the flow label, for example, field in the IPv6 header. And this allows us to basically seamlessly integrate a core domain to the data center domain without the need for complex functions such as data center gateways, which we use to bump an IP fabric into the MPLS fabric. That's not required anymore. Also, it allowed us to simplify the overlay model and get rid of some of the overlay encapsulation, the likes of VXLAN, the likes of IP and UDP, and the likes of NSH. All of these functions and complex functions and hierarchical protocols have been eliminated by just using IPv6 encapsulations. So at the heart of SRv6, we have the IETF proposed standard RFC 8986 that defines the segment routing network programming concept. So that's the concept we use to encode what's called a network program. The network program consists of a list of segments or instructions. The instructions are mapped to functions. Those functions are mapped to possibly everything, but they are defined in the RFC. Things like we can map a function to a VPN, VPNv4, VPNv6. We can map a function to do something inside the VPN itself, like doing a routing lookup or bump the traffic to an egress interface with specific quality of service. We can make an action or take action to, or map the instruction to a function, or the function to a layer 2 VRF to do a MAC lookup, or to bump the traffic out to a VLAN interface. We can map the function to something like a VNF function or CNF function or Kubernetes cluster. We can map it to something like a P4 code on a Silicon One. We can do a lot of things. And the idea of the standardization of this behavior is to be able to create an overlay model that's interoperable with underlay optimization. So all of this we are doing by just encoding the packet, the network program with list of instruction in the packet header without creating any state in the network. So unlike the RSVP and other transport protocols that creates a lot of state in the network and limit the scale of the network, in segment routing architecture, we don't have any state inside the network. Practically speaking, you can basically have the network program processed by a non-SRv6 node in the middle, like a core node, without being aware that this is an SRv6 encapsulation, because it only needs to look at the destination field of the packet. And this allows us to do what? To build an end-to-end fabric that is stateless and enable ultra scale for the transport network end-to-end. So another RFC that's basically a pillar in the SRv6 architecture is a segment routing extension header, which is RFC 8754. And this is where we basically show how we encapsulate the list of segments or the network program into the IPv6 packet header. That's not something new. That's the routing extension header has been ratified in RFC 2460. That's defined 20 years back, the first RFC for IPv6 protocol specifications. And it ratified again or updated in RFC 8200. And so basically that's not a new concept. It is a concept that we defined very long time back, and we make use of it by defining just a new type inside the SRH, which is type 4, to encapsulate the list of set. So the header, as you see, is very simple. You just have a tag to can flag some flags like the O and the M to sample some packets. Then we have the list of segments included as 128 bits inside the segment header. And we have a segment left pointer that basically points to which of this segment list is active now, so it gets copied to the destination header of the destination address field of the outer IPv6 header. And we also have a metadata TLV, which can be used to do to post, for example, security policy or security signature for the endpoints to process it once it's received. So this simplicity in terms of data plane forwarding and control plane allowed us to be able to stitch or create a stateless fabric all the way from a socket on an application or container or VNF, all the way to a peering point at the border of the network, crossing all the domains in between the likes of the metro, the lack of access, aggregation, and core and data center without having any stitching. So this is what we call the zero stitching end-to-end transport. So many of the challenges that we have been we were facing with the MPLS, and we get used to it with the MPLS, have been solved by native capability in the SRv6 architecture. Things like the ECMP. We used to suffer from ECMP and the core nodes because the label stack was deep, and the node needs to go through all of the stack to be able to do hashing and calculation to perform ECMP. Now that's not the case. We have the ECMP hashing or the function itself encoded into the flow label in the outer header, so any core node that support basic IPv6 function can do optimal ECMP. Or the inter-domain routing functions that we used to suffer from and used to have very complex protocol to connect the access to the core. The things like the seamless MPLS, for example, have been replaced, and now we can have inter-domain routing with normal prefix summarization without losing any of the high availability or redundancy functions. The likes of the BGP PIC, for example, it's completely working with this summarization. And here is more details about the technology which you can use and you can find on the segmentrouting.net, the same website I pointed to or referred to at the beginning of the slides. So deployment status, in terms of deployments, we have a record speed of SRv6 deployment exactly the same way we had with the SRMPLS. So today we have commercial deployments that has been in production for almost 3 years, since 2019. And we have other deployments that's non-Cisco or Cisco plus other vendors as well. And it's almost 100 deployments with 100 million subscribers being carried over SF6 transport networks. These deployments taking place across different segments, not only in SP, unlike the MPLS, that taking place on SP network, on multiple segments within the SP network, and on web scale networks, data center networks, as well as in data center and enterprise domain as well. Here is the list of customers that either deployed SRv6 or testing SRv6 or planning to deploy SRv6, with blue ones are the new one to the list. So from a technology point of view, we are committed to all the operators who adopting the SRv6, that to make the technology standard, not to make it something proprietary for Cisco only, no, to create an ecosystem for the technology, to make it interoperable, interworking with other vendors, and deployable in a seamless way in the multi-vendor environment. So we created a very rich ecosystem, as we are going to see in the next slides, that include hardware vendors, software vendors, silicon vendors, as well as open operating system and application vendors as well. So from a standardization point of view, we have the full confidence to say that today the SRv6 is very matured when it comes to standardization. We already had 3 RFCs for covering the SRv6 architecture. The main one is basically RFC 8402 that covered the segment routing architecture in general with 2 data plane, the IPv6 and the MPLS. Then we have RFC 8986 that defined the network programming concept, which I described 2 slides before. And we have the third RFC was basically the SRH, that's RFC 8754. But more recently, we got basically more RFCs moved from draft to standard proposal RFCs, the likes of the SRv6 network programming, or the likes of the SRv6 BGP extension that get rid of the MPLS or the VPN label at all, and use IPv6 as identification or function, and the likes of the SR policy architecture to standardize the syntax semantics of the segment routing policy, and ONDM as well. So if you look at if you are monitoring how fast the standardization going for SRv6, you will notice that it is going much faster than the norm at IETF, which is a big sign and a good sign for the endorsement of the SRv6 in the industry. So from an ecosystem point of view, as I said, we are not making the technology only for Cisco. We are committed to make it very rich and very multi-vendor by default. So we have a lot of, as you see, we have a lots of vendors supporting SRv6. All the major vendors, the likes of Juniper, Nokia, Huawei, ZTE, and Arcos as a software company or NOS company. Cisco, it's being supported on multiple silicons, merchant silicon, the like of the DNX family Jericho 2, the likes of Cisco Silicon One, and custom silicons from different vendors as well. Unlike the MPLS, with completely different picture here, that you never see applications and open operating system or software vendor supporting or part of this logo slide. Now, it was SRv6 because of simplicity of the SRv6 and the use of IPv6 as data plane. It's now supported by a large ecosystem of application and network operating system, the like of Sonic, the like of OpenStack and Kubernetes, and FDIO and the Linux kernel. So we had done many successful interops with the ANTC between multiple vendors. That is to prove that the technology is multi-vendor, it's not a single vendor, and we covered most of the use cases that the customer are using in this interop test, and we have the links here to refer to this testing. We participated in all the interop tests except in 2022. We didn't participate due to COVID travel restriction, but there was no difference in the use cases tested in that test compared to 2021, and we are committed to basically participate in all the coming interops. So the links are here. You can go through the use cases and select the vendor of choice to see how he did in the NTC report. So one of the main topics we want to cover here is the microset, which is new mechanism added to the SRv6 architecture. So SRv6, you said, you will find different names. Commercially, it's known by microset or microsegment or SRv6 USED in brief. At the IETF, you will find the name a little bit different. So you will hear next, next C or next compressed SED, or next in general. What is it? It is basically a mechanism to compress the list of segments encoded into the packet header to optimize or to reduce the transmission overhead. So the segment or the instruction is encoded as 128-bit like a normal IPv6 address, right? So when we add more of this with very long, deep list of segments, we basically consume more bytes out of the total MTU allowed on the network. So what we did is basically we tried to compress the list of segment by dividing a single 128-bit IPv6 address into multiple segments and use the first 32 bits, which is not fixed. You can use last 16, you can use, first 16-bit, first 48 bits. But what we are showing here is basically the first 32 bits are used as microset block, and then we use the remaining bits for different segments. So instead of encoding a single segment as 128 bit, now we are able to include 6 segments in just 128 bit. This means what? This means a lot of reduction in terms of MTU for the transmission of the SRv6 encapsulated packets. So we have managed to do this without changing anything on the architecture. So and really nothing changes to move from basically a native SRv6 encapsulation into microset encapsulation. And you will find the SRH standard exactly works the same way. You will find the network programming exactly the same way. It is just an extension to, it doesn't need any IGB extension. It doesn't need any other protocol extension. It just needs what we define is a new behavior part of the RFC 8986, an extension to that RFC to basically add more functions and new functions, a couple of functions, which is basically the shift and forward function that can be done by any IPv6 capable node or software. So this is a comparison between how if we include the network program with a list of SED into the packet header using something like the native SRv6 encapsulation or using the microset. On the x-axis, you find the number of encoded sets. On the y-axis, you find the number of bytes consumed. And here, as you see, that we can encode 10 sets if we encoded as 128-bit in the header. We will end up with 208 bytes of header. But if we include the same number of sets using the microset, the compression approach or mechanism, we will end up with 64. That's a 69% decrease in the transmission overhead in general. So it's a big achievement, and it is something that's not critical, it is deployed. So we have this deployed on a few accounts, big accounts indeed. So the likes of Rakuten have deployed this to realize end-to-end 5G slicing, where we need a very deep and very large stack to get your traffic steers through things like G-island services, virtualized G-island services, the likes of DBI, CGNAT, firewall, water filter, you name it. And we also have deployed this in BID Canada as well. There are some links here. Again, I'm referring to the segmentarchive.net. It's a very rich web interface or website that covers most of the information we're covering here, so you can get to it. You can visit to get more information about it, about the use case exactly. So again, the microset has a rich ecosystem. It's supported by multiple vendors, software vendors, and multiple silicons, merchant silicon and custom silicon, and multiple softwares, as we always committed to do. So you can find more information and actually a demonstration for how it works exactly and the difference between the native encapsulation and the microset compression encapsulation or encoding. You can find it and this at the segmentarchive.net, and we have presented this at the recent Mobile World Congress that done last year. So now another feature that we have recently introduced to SRv6 is basically the bus tracing, and this is an interesting one. So in every SP and web or data center network, it is likely to find ECMP. ECMP is there for many good reasons. It could be to increase the capacity. It could be to reduce the blast radius of failure in the network. It could be you are building the network as a fabric using disaggregated chassis, or you are using system on a chip. For many reasons you have ECMP, but ECMP is a fact in the ground. We know that you have ECMP. What you don't know is which path your traffic is taking, right? So, and if there is a FIP corruption or there is a bug, you don't know if your traffic or packets are drifted away from the ECMP path or not. You don't know this. And you still don't know this until you have a complaint from a customer or an outage that there is an impact on the packets going through your network, there is a delay increase, or there is some SLA violated because of this. So what we are trying to solve is basically how can you know which path your traffic is talking. And here I'm not talking about any over-the-top robbing, because over-the-top robbing will tell you there is a problem, but it will not tell you why there is a problem and where is the problem. But what we want to do here is basically to make something, give you the visibility, which path your traffic takes across the network and how long the traffic takes in the network, the exact data plane delay, and what was the load in the network at that point of time. So that is something that we are trying to solve. But while solving this, we had to come up with objectives, right, to make it something doable. So the first objective was we need to do this as a stamp on the packet header. We don't want to create a state in the network. One of the fundamental aspects of SRv6 that we are building a stateless fabric. We don't want to create any state in the network. If you go to the core router, you don't see all this. You don't see all this information. So you can scale the core router. Sorry, let me just. We also wanted, another objective, we wanted to implement this in the hardware with the basic pipeline macro instructions. So we don't want to offload or bound the traffic to any CPU or coprocessor, line card processor or something like this. Because if we do so, then this is not the exact path your traffic taking. Your traffic is being forwarded by the pipeline or the ASIC or the MPU. So we don't want to offload this to any of the coprocessors. We want to make it very MTU efficient, so that's why we put it as target. We will consume only 3 bytes per hop to stamp the packet, to add the interface load, and to add the latency as well. And we wanted to make it workable with legacy nodes who just support SRv6. So what we did is basically we used one of the old IPv6 extension, and again that's back to the power of using IPv6's data plane, because IPv6 is rich since very long time. What we are doing here is we are consuming or using the features and capabilities that has been ratified in RFC in the IPv6 standardization or standards 20 years back. What we are using here after the IPv6 encapsulation header, we are using the hop by hop header. The hop by hop header is one of the extension options header that's exists in the IPv6 standard for 20 years, and it's mandatory for all nodes to process this header if it exists. And we put it before the SRH. So we put like a metadata called the MCD, or the mid-byte compressed data, into the hop by hop. So each router in the bus will stamp his information into this header by just using 3 bytes. So he will shift 3 bytes and will add information for his own timestamp, interface load, and outgoing interface on the header. So the first router is the ingress router, who has the ECMP, will generate the traffic and will use the hardware pipeline to get this traffic, and will do all the entropy and hashing to use all the ECMP at the same ECMP passes at the same time, and he will stamp his information and the SRH, TLV, and UTLV added for the pass tracing. The second one is intermediate point. He will stamp his information in outgoing interface ID, outgoing interface load at the time the packet exit the interface, and basically the time stamp of the router. He will add it to as an additional information to what the ingress router add. Again, along the whole bus, it might be a very long bus, the router G will do the same. Once the traffic reaches the exit router, which is basically the sync router, we call it the sync router, which is router M, he will do 2 things. He will destroy the first, the outer header, which is basically specified himself as a destination. He will add a new one. He will stamp his information into the MCD points or metadata, and he will encapsulate this with a new IPv6 header and send it to analyzer. Then the juice at the analyzer. So at the analyzer, we have now an end-to-end pass, the exact pass your traffic is using, with end-to-end delay, real-time delay, with the load of the network. So we can give you this as for just visualization, or we can take it to do very useful things. We can take it to compare the actual forwarding in the network against something like the calculated using the IGB, like the BCE, for example. So this is the IGB pass, this is the actual pass, if there is any discrepancies or difference. So you can compare, you can point any actually misbehavior in the network, any spikes in the network, any packets that get drafted from the ECMP. All of this you can do with basically a basic IPv6 encapsulation. Again, this is something that's not coming. Sorry. So this is something that we are shipping in 2022, and it's being supported on almost all the silicons we are shipping to the customers, including the Lightspeed silicon on the SR9K, the Silicon One Q200 on the 8000, and the Jericho 2, which is a merchant silicon that we use on our NCS platform. And it's supported as well by other open source ecosystem. And this is a draft that we are submitting to the ITF, and we're working to move it to RFC soon, inshallah. So at the end, I will leave you with a couple of references for how to get in touch with us, and a couple of books that have already published for segment routing architecture in general, and there's a new one coming for SRv6 in particular. With that, I'm done, I think, on time, so happy to take any question if any.